So in this lecture, we're going to look more at strategies to speed up your computation. And we're going to do this through parallel processing, so making use of multiple cores on your computer. Even basic laptops now often have 4 or even 8 cores. And then also more conceptually, although we won't implement this, we'll look at the MapReduce framework, which is also a way to make use of multiple cores or multiple processors. So how to do this on your local laptop or your desktop computer? As I mentioned, even basic laptops have multiple cores. And some functions in scikit-learn actually make use of this already, implicitly. For example, there's an njobs argument to some of the classifier functions that you can set to use multiple cores. Njobs equal -1 does this for you. Databases, which we'll talk about in the next lecture, also make use of multiple cores to do CPU-intensive operations like spatial joins. And again, we're going to look at this in the next lecture. But in other cases, you're going to need to do the parallelization yourself. And Python can do this through a library that's called multiprocessing. And the intuition behind this is you set up discrete processes or functions, and then each of these functions can run on a separate core or a separate processor, and then at the end you bring these all back together and merge your output. So let's recreate the example we used in Module 4, where we're calculating the distance from every census tract to the third closest food pantry. As a reminder, this is a common measure of accessibility. Look back at Module 4 if you don't remember what we were doing there. So we've seen this code before. We're going to use SenPy. We're going to use the request library to import this. This is actually in your GitHub repository. And we're going to restrict the pantries to Los Angeles. And we're going to create a geodata frame with the food pantries in LA. And we're going to convert these to this California state plane, the correct zone for Los Angeles. OK, so we have our census data frame and we have our pantries data frame. So now let's try and slow things down. Let's make 100 duplicates of this pantries data frame so we can see what speed improvement we get from parallelizing our code. So here we're going to use a list comprehension. We're going to loop over 100 times and then create an extra copy of this pantries. So we'll create a list of 100 copies of this pantries object. And then we're going to concatenate them into a single geodata frame. So we have much more. We have 2.4 megabytes of data and 21,000 rows rather than 211 here. And now this is the function that we used before. So we're getting the third closest distance. So we're computing the distances from each pantry to the census tract geometry that we're passing in as an argument to this function. So for each census tract, we're going to get all the distances to every pantry. We're going to sort these distances, and then we're going to take the third one and return third closest. So how long does this take to run? OK, so this took 54 seconds. So you might not be worried too much about this. It's certainly not parallelizing just to save a minute. But if you're doing this for all census tracts and all grocery stores in the country, maybe you do need to speed this up in order to have it run in a reasonable amount of time. So let's see if parallel processing can help. So don't worry too much about the syntax here. There's lots of examples on Stack Overflow and other places when you need to use this. But I want you to understand this conceptually. One complication of multiprocessing in Jupyter is you have to actually import the function from disk. You can't define it in a cell. So if you look in your repository, take a moment to see what this parallelization example.py file means. It's basically just going to contain this function above. So I saved it, and it's exactly the same, except there's a second argument, pantries. Because this means that the function has to be self-contained. You have to pass all the arguments that it needs, rather than relying them on being available as global variables in Python. So how do we do this? Well, let's import our multiprocessing library. and the functools partial we'll explain in a moment. And then let's import our third closest dist function, which is in your GitHub repository. Now we're going to use 4 cores here, 4 processes. So our partial splits the function up so that pantries is always passed to this third closest distance function. And then I'm going to pass these geometries, so tracks geometry, to our function, but it's going to split these up over multiple cores. So basically I'm creating this pool of processes, and each time I go down an element in my tracks data frame, it's going to say, okay, I'm going to pass the geometry to the next available core, and when it's freed up, it's going to ask for the next one, and so on, and so on, and so on. And then it's going to return these in our results list. Okay, so now it only takes 17.5 seconds. So it's not a 75% reduction, because there's some overhead with creating the processing, the multiprocessing. But using 4 cores only means about a 2/3 speed up rather than a 3/4 speed up, but it's still pretty nice. And importantly, multiprocessing works here because none of these jobs are dependent on each other. These different cores aren't having to share information across each other. Each tract is its own independent calculation. So how do I access our results? Well, it's in this results object. It's a list. Let's look at the first 5 elements. Okay, so these are this first census tract. The closest food pantry is within the tract. It's a 0 distance. For this one, the third closest is 589 meters. We have 749 results. It's the same length as our original tracks data frame. We had 749 geometries to process, and our function returned a distance from each one. So let's just add this back to our data frame, and we can see we've added this new column here with our results from our multi-processing. We can check and make sure this is the same result as we got without parallelization, our results above. So that was a super quick tour of how you might implement parallel processing on a laptop. An analogous way in the cloud is called MapReduce. And we can see the details of the algorithm here in this Wikipedia page, which is a nice introduction. But in short, there is this map stage, which filters and sorts. And then there's a reduce stage, which reduces the input data to something smaller. And each of these mappers and reducers can actually run in parallel. They're independent of each other. So imagine you have some input files with a list of words. Now we're going to split up each line and pass it to different mappers. So this first line is going to get this mapper. And then it's going to split, this mapper is going to create this individual words. And then there's a sorting and shuffling phase. So we move all the apples from these different nodes and sort them to apples. And then we reduce it. We create all these apples and we combine them. And here we just want to do a count. So this is our reducer nodes here. There's an apple reducer node, there's a grapes reducer node. So a super simple reducer, but you can imagine more complex operations on these sorted values. And then it creates our final output. It's normally done in the cloud. There's specialist tools, things like Hadoop, as they're called. But you can also do it on a local machine in Python as well, if you really want. But conceptually, with any multiprocessing algorithm, the key thing to think about are there discrete, independent chunks that you can split up your tasks into. The final point I'll make about speeding up your code is when you outgrow your local machine. So almost all of my own data science work is run locally on my office computer. It's a 2018 Mac Mini. My previous desktop was 10 years older than that. So you don't necessarily need a lot of computing power to do most tasks. Maybe you need a really large external hard drive, but those are pretty cheap compared to buying a really fancy computer. Sometimes this takes a few days, sometimes it takes a week running in the background, sometimes you have to parallelize, sometimes you have to be judicious about data types. But for me, that is easier than uploading to and paying for a cloud service provider. but for some jobs you're going to outgrow your laptop or your desktop computer. And we're not going to say much more about options in this course, but I just want to introduce them generally. So in general, there are 4 options. You could beg, steal, or borrow. Can you get access to a computer in a GIS lab to run over the weekend or over a holiday? A cluster computer at UCLA, it's called Kaufman 2, and you can run pretty much any Python code as a batch job. Your job's going to be queued until there's resources available for it to run. And there's cloud-based services like Python, Python services like DeepNote, or Python Anywhere. And the amount of memory and compute power for these varies, but generally you just pay for what you use. And then there's general-purpose cloud service providers like AWS, Google Cloud, and so on. These let you run Python and pretty much any other open-source tool, including databases, which we're going to talk about in the next lecture. So these options are changing over time, so keep an eye out for new firms and services that are being offered. The takeaways that I'll leave you with. Parallel processing works when you're applying an identical function to many different inputs. For example, census tracts. You want to run the same operation on every single census tract, or the same operation on every PDF files, or another large pandas data frame. There cannot be interdependencies between your jobs. Often you can run these on a standard laptop, but if you need them, perhaps that's a time to scale up to cloud service providers or cluster computers.